Last segment we discussed about the moment of a force about a point, and we saw that the most general form in which we should be able to calculate that is R crossed with F, and the situation was like this. There is a plane. In fact, the plane need not be there from the beginning. Once we have a point P and a force F, these two entities, they should define in fact the plane as soon as we define. Otherwise P and F should be in any general plane, general space, and then we said that this R, now we could draw the R to any point on the line of action of F, and this R cross F will give us this. And just I just want to show that the direction of M will be perpendicular to this plane, and this will be something like this. Say, okay, this is M P. Now one more step, if we move, we will actually introduce one more very interesting building block, and that is the moment of a force about an axis. Okay. Now this concept in our sequence of important vectors, it will come as I think number 5. Okay. Now how to define this? Let us first define this properly visually, and then we will see how to evaluate it. Now for that, let us have a given axis like that. Let that be denoted by A prime, and now you have a force randomly situated with respect to this axis. For example, like say this is F, and we are supposed to find out the moment of this force about this axis. Now what it does is it's basically evaluating or giving us the turning effect of this force about this axis. Just compare with this example. So this vector MP was giving the moment of this force about a point. Now we are asking about an axis. Okay. Now so the idea is, if we create maybe a surface, so like that, which passes, okay, let me okay, how will I erase it? Um, okay, I want to actually make it dotted in a way, so I'll do like that. So in a way, for a mean is this portion is behind the plane. Okay, so in fact, say let it be this. Okay, that means at this point the axis is just piercing through the plane. Let the plane be called, say, plane A maybe, and at this point, in a way, it's bad, somewhat like this, yeah. So imagine there is a small perforation on that plane, and this axis is piercing through that plane. Okay. Now, and this f is in fact coming out of this plane at some random angle. Okay. It's so note that this is not lying on this plane, means not necessarily lying on this plane. Now, to visualize the amount of turning effort that this force is having about this axis, what we need to do is, first we have to create a the component of this force in this direction. Okay, so let's draw. So this one, no, it's bad angle of drawing. So it should be parallel to this. Still, it's not parallel. At least it should be visible. Sorry for that. Now, this is the component of f, which is perpendicular to this plane and parallel to this, because anyway this plane is perpendicular to this, so we had taken like that. And okay, so that also I should visually represent somewhere. How do I do that? Maybe at this joint this is 90 degree. Okay, so this is perpendicular to that. And similarly f, I'll say vertical maybe, yeah, f vertical, shall I use the color? F vertical is perpendicular to the plane and parallel to the A prime axis. Now, as soon as you draw that, you will get two vectors f and fv to define another plane. Okay, let that plane be denoted by maybe what? How should I do that? Maybe like that. It's coming like that. Okay, so like that, something like that. And basically what happens is you have like this maybe. Okay, so this much is, sorry, I should have drawn like that. Now, this is the line along which should have this, So, this is the line on which the plane B, I'll name it say plane B. Plane B crosses or intersects plane A along this line. Let me also do this over here. It's not visible this much, like that. Is that fine? And both FV and F are actually lying on this yellow plane. Okay. Now, what happens is you now get a plane on which you can now resolve this F to show the other component which is perpendicular to FV, and let that be shown as maybe this. At this point I can just show like that. Okay. So, this I will denote as F horizontal. Just randomly I am denoting. Okay. Now, so these are the three components which we have now systematically resolved F into. But then we get a distance here, this distance. If this vector now, this line is having a perpendicular distance, the shortest distance somewhere. Okay. This is the distance D, because this line will pass above or below. In this example, it is passing above the A prime axis, and the distance at the point where they are nearest to each other, let that be D. Okay. Then this moment of a force about an axis, so which I will call or denote by, say, F A prime, not F, sorry, I will denote, because it is moment, I will denote by, so here again it got, yeah. So, I will denote by M A prime. Okay. So, that will be this component which is F H times D, I mean this magnitude of that force times D. So, that is the moment which basically, and it is the magnitude in fact, because this side is also a magnitude. So, this is the physical meaning of the phrase that moment of a force about an axis. Okay. Now, so this should be completely first understood, and then we will try to see how to evaluate this in a much effective way in most general sense. Okay. The way we did this, because if you remember, we had even this sorry, here I should have even put that, we had this, this also was there, and then we came to this form which is more general, which is applicable in most general cases. So, same thing here, we have understood what is the physical meaning of this, and now we will go and see how to evaluate that. And before that, I will just tell you what the form will come to, and so that is equal to something like this, say R crossed with F. Again it has got very similar form with this, and dotted with N. Okay. Now, there are some natural questions which will come up. What is N? What is R? Because on this diagram we have never shown these two things. Only thing which we have shown is F, nothing else, because we were just trying to understand what physical quantity is being represented by this. So, try to see one more point which is very important to be observed is when we resolved f in these two components, this line does not look like that it's perpendicular to this because of the inclination of this plane, but try to see that this line or the vector fh is also lying on this plane A, the orange plane. So, that means, and then the orange plane is perpendicular to A prime. So, it must be perpendicular to that, right. So, that is how we get this the physical meaning that this component, the vertical component of f, does not contribute towards any rotating efforts from the vector f. The part which is contributing to the rotating effect is this fh. Now, how to get that portion fh is by this. Okay. So, we are basically defining the vertical force, and the vertical force and the original force then define a plane, and on that plane this will stay. That means, we will resolve this force on that plane, and then the distance of this line will give you the moment arm basically. Okay. But now let us see how to use this, and why should it work. That also is a very important question, that why should this formula even work, and then what these terms are R and N. Now, let me show those terms on this picture itself, and then we will go for the derivation of this. Now, this R is defined like this. You take any point, again mark it, any point on the axis A prime about which you are evaluating this moment. So, that is one of the powers which you get. Okay. So, as soon as you get some freedom, that gives you a power, that is the strength of the method. And from that point which has been picked now very arbitrarily on the axis, then you have to, so this is the line of action of f, and you draw any line from that point to the line of action of this force. Okay. And that will give you R. Okay. So, that gives you the freedom, that gives you the strength. Okay. Choose any point along the A prime axis and call it, say, the origin O. From there you draw a displacement vector calling it R, which joins the point O to any point on the line of action of f, and then you get this cross product R crossed with f. Okay. And now, what is n? The n is the unit vector in this direction, say maybe, yeah. So, this direction unit vector, the A prime axis is represented by the unit vector n. Then, so what it tells you, that you calculate this cross product which will be a vector, and then dot it with the unit vector in the direction of A dash, which will give you a scalar quantity, and that will give you the amount of moment. Okay. I am emphasizing the word amount because it is going to be a scalar quantity, because the direction anyway is fixed, the moment's direction. Here the moment's direction was also not fixed, because f was an arbitrary direction, p was arbitrary direction. You had to even calculate the magnitude and direction both for the moment mp, but in this case the direction is completely frozen once you fix the axis direction a prime. Then you evaluate like this. But then let us see why should it work. Okay. Okay. Now, let us see. Suppose this is the axis which you have had. Let me first draw the maybe this plane. Okay, because we have to now, and then let me draw the axis. Like that, say this is a prime, and then let the origin be somewhere here, O, and let us take the x axis of our set of axes in this direction. Let this be x, let this be y. So, this will come out to be z. Okay. And we have chosen O somewhere randomly. Okay. There was no restriction on where to put O. That's the power which I mentioned in the this point O. We could choose any point. So that's why we have now chosen the origin of the axis to be anywhere. Now, let the force which is acting at the point here may be given like this. Okay. Now, what we do is we will resolve this f along the three components in the direction of x, y and z, and then before that let me put even the ijk's in this direction. This is I, this is j, our unit vectors have been fixed, and k. Okay. Now, if I have to resolve this in three directions, let this be not that much, maybe this much. Okay. So, this is say f x. Yeah, so this was a vector. Now, this side is f x, and f y is this maybe, and f z may be like this. Okay. Now, to calculate the moment, what we need to do? Let us see about the AA thing. So, now let be the point which at which this plane intersects with this axis be say this one. Okay. Now, so the x coordinate of this point is this much. Let me right. So, this is the x coordinate of that, and then on that plane you come in the y direction like that. Maybe we will not reach that point. So, it may not so happen. It may so happen that we come like that, to some point say here. So that may be your y, and then you go up in the z direction. So this is the z coordinate. So I'll do like that. Z coordinate, this is the y coordinate, and this is the x coordinate of this point at which the force F is acting. Okay. Now the vector r was from this, this point, right? So along any point along the line of action of the force, let that point be this now. So this is our r. So according to this picture, r can now be written as xi plus yj plus zk, right? So the position vector of the point r is xi, yj and zk. Is that fine? Now how do I get it? To be consistent with all positive direction to be positive, let me do one thing. Now this fz, I will call as in the positive direction, so that all positives will be okay. Now I'll draw that in the positive direction. Okay. Let this be the fz component. So this is fy and fz component. So that whatever formula we will get, all the positive senses will be positive and negative are negative by default. Done. Then let us calculate the moment of all these components about the line AA prime. That will be the moment, right? So now what will be the moment of fx vector? That's 0, because it is parallel to the AA prime direction. So it will not contribute any moment. Then what about fy? So now suppose this is fy, it is in the negative x direction. So the contribution is negative. This is the height z times fy. So that is what I was meaning, that I have taken all positive direction fx, fy, fz, so that the quantities will be looking nice, and then once you get that, that will be valid for any direction you choose, or the component when they come in any direction. Okay. Yeah. So now so this z times fy, okay, then fz is in the positive direction, and its moment arm is y. So y times fz. Okay. So this is the full component, full amount, which will be the rotating effort or the twisting effort about the axis AA prime, because these are the only 3 components of F. This has got no contribution, and the contribution from these 2 forces are given here. So that's the full thing from component side. But then we had also calculated earlier the moment about this point, how to calculate that, right? We saw that in the previous section. So this I will now denote is say with m a prime, okay. And now let us calculate what will be the m about the point O, the vector. So that will be r crossed with f, right. So how do you calculate that? It will be say r is this and f will be, say now f will be fx I plus fy j plus fz k, right. So this will have three terms. The first term with I plus some other term plus times j plus some other time k, right. Now this one will be what? In fact, this will be, if you calculate the cross product of this, you will actually get this. Sorry, this should have been y, right? And here you will get x fz minus, sorry, z fx, then maybe the signs are different, it will come like this. I'll change it, okay. So it will be z fx minus x fz, and then here it should be x fy minus y fx. Is that fine? Yeah, I think so. Yep, fine. Now that is the moment of about this point, okay, and we know how to, what is the meaning of this. But then you see here, this term is nothing but this, isn't it? Y fz minus z fy, okay. So here somehow it's missing y, okay. So that means how do you get this term? By so this is nothing but, if I take this m o, I'll dot with I, then these terms will just vanish, fine, and only term which will survive is this, and I will get this, fine. Now because we had taken x axis in this direction, so we had to do this dot product with I. Had this been any normal vector, unit vector n, so the formula which we had written, here just comes up. See, r cross f dotted with n. So that is what we have got. So this is nothing but r crossed with f dotted with n, right. So that's the proof of how to get this physical quantity which we had discussed here. So in summary, what you have done is, or from the beginning, you had an axis, you had a force, okay, randomly placed with each other. Now then how to calculate its moment about this axis? Pick any convenient point on the axis, call it O. From there, draw a displacement vector to any convenient point again on the line of action of force F. Then do the product, the cross product R cross F, then get the unit vector in the direction of A dash, then take this dot product of R cross F with N and you will get it. And this is how the derivation looks like. Does that make sense? And yeah, so see here, why the choice of O, why didn't it even matter? Because in this expression you see the x term is nowhere coming into picture. When whatever you pick, whichever point you pick there, it never comes up in this thing. So that is why you are completely independent to choose that point. Okay. So that was about our fifth spatial vector, and in the next segment we will see another very beautiful spatial vector, which is the couple moment.